ladies and gentlemen, welcome to the FS Elite Theatre in preparation for your talk with ToLiss. So just a few housekeeping things before we do begin. There are 4 exits in this building. There are 2 at the top, and then there are also 2 down here. Once this presentation has finished, if you do wish to leave, then please do walk just down the stairs and exit towards here. Please don't go back up towards, so we can have a nice one-way flow. And we will also take some questions at the end, so please do hold anything for Torsten at the end. But for now, please do put your hands together for ToLiss, who's going to talk to you about Airbus aircraft.
Okay, hi guys, my name is Torsten, or Gliding Kiwi in the Org Forum, and I want to thank FS Elite for giving us the opportunity to talk a bit about our company today. And what I've prepared for you guys is a bit the history and like the highlights of what makes our product special. So when it comes to history, how did it all start? And I think in our case, you can sum up the motivation with a single picture, which is this. I was living in New Zealand when Air New Zealand received this aircraft as their very first Airbus A320, and I always loved A320s, and it was Lord of the Rings hype. So when I saw that thing and I came back home, I thought like, I want this on my flight simulator, and it didn't exist. So I thought, come on, I'll do it myself. How hard can it be? So that means I started playing with PlaneMaker and X-Plane 8, trying to replicate that thing. And well, I was working at that time at Airbus in parallel, so I didn't really have that much time to do things. But then 2008, I decided, come on, I'll do a PhD in flight controls, because I wasn't really impressed by what I was doing with my professional life up to then. And suddenly I had a lot of time. So then the development of the aircraft really took off, and the Airbus fly-by-wire plugin, which we're still using today, started really to grow until in early 2009, we finally released the first freeware version of the QPAC A320. Anybody in the audience who still remembers that? Like that's, I mean, it's 15 years ago now. Anyway, so that was like a 2D panel, very basic 3D cockpit, but it had already a full-grown fly-by-wire system with all the protections in it. And yeah, that was really the start where we got going. Then any PhD ends at some point. So in 2012, I was finished with that. First kid was born, second kid was on the way. And then the big question was, okay, what am I going to do now? I'm going to have 2 kids. I'm going to start working again. Is this actually going to continue, or is it going to stop? But of course, I'm standing here today, so we did continue. And all of that led to the first release of our first payware product, the QPAC A320 version 2 in 2013. That was at that time for X-Plane 10. And it was still with a 2D panel. So what it looked like was this. Like, I mean, when you see, we've come quite a long way since then, I would think. So we had like this nice 2D panel with like pop-up pedestals and stuff like that. And that was a 3D on the outside. So not quite up to 2024 standards, I would say. Anyway, that was our start. Then this development slowly started to get better and better. We got a deal with Flight Factor to provide the fly-by-wire and FMGS suite for their A350, which was initially released in 2014. And we had also made a deal with Flight Factor. Okay, we need to get the QPAC better. We want to have a full 3D model in it. So why don't you guys provide the 3D model for that? And that was planned at that time as a QPAC version 3. So however, QPAC version 3 never came to light, because in 2017, due to unfortunate events, the person I worked with at QPAC unfortunately passed away. So we had to get out of that. We ended up founding our own company, Juliana being my wife and me. We founded ToLiss, we purchased the rights the QPAC had on our software from them. And from then on, we started developing on our own, which finally ended after about 15 years after I started, with the very first ToLiss product, the A318 version 1.0 on the 28th of February in 2018. So since then, we've increased our portfolio a little bit. So we have 4 additional products to date. 2 years later, exactly to the day, we released the first A321. Then we came out with the A321 Neo add-on about 9 months later. That one allowed you to add like the Pratt & Whitney engines, the CFM LEAP. It also has the the long range, the extra long range variant, so you can have all the different fuel configurations. If you select the XLR, you have 33 tons of fuel that you can put in. The regular A321 has like 18, so it's like a significantly higher amount. And also the door concept, if you've seen like A321neos, they exist with all kinds of weird doors. You can have 2 overwing exits, you can have 1 overwing exit, you can have a door behind the wings, you can have no door behind the wings, etc. We support all of that, so you can really configure the aircraft to the airline you are trying to fly. And then after having done 2 single ALs, I thought like, okay, come on, it's time to do something bigger, a long range aircraft. And my personal favorite, just from the looks of the airplane, from the aesthetics, has always been the 340-600. So we've decided to launch that one. And that one was finished October 25th, 2021. And that date actually is exactly 30 years anniversary of the first flight of the Airbus A340. That's how we picked our release date at that time. And then the most recent addition was, because we have the 319, which is a CEO, the 321 base package is also a CEO, so classic engine option. We've decided, okay, we also need to do this 320 Neo so that you have somewhere where you just buy the one package and you get the full set of Neo engines. So we came out with the 320 Neo on March 20th, which, with a weird way the Americans write the dates, is 320. So that was our driver for that release date. And yeah, and that one has, besides the new engines, it also has a lot of newer avionics features like satellite landing system, FMS landing system, and many other things that you can enjoy in a real life A320neo. So that's a bit the history of our company. Now I want to move to like what makes our product special. And one of the things we really focus on in our development is always the handling and the performance. So in order to get that right, in the meanwhile, since X-Plane 12, we've basically transitioned to having our own custom engine model. So rather than spending a lot of time tuning the X-Plane model and tuning it again and again every time X-Plane changes it, we said, look, we'll get independent of that, we do our own, then we can tune it exactly to all the data that we have, get exactly the right fuel burn, the exact right thrust per N1 for the different flight regimes. And most importantly, we are independent from other people changing things on their side. So our model is always going to give you the same result. Whether you fly an X-Plane 11 or an X-Plane 12, you'll get the exact same thrust, the exact same fuel flow, the exact same EGT, etc. And we really compute in the end. We take the airflow, we compute it through the cold duct using the compressor fields, as you can see up there on the right side. Do I manage to get the mouse there? Yeah. So we use this thing to compute really the flow through the duct here. Then we also compute the flow through the hot circuit in order to get like the bleed pressure, the EGT and things like that. And that really gives overall a very good, very realistic representation of the Airbus engines. And the second thing that we've also done, we had this for a long time in our products, is we have like a custom drag model. So I'm a big fan of the X-Plane flight physics, which is the reason why we're using X-Plane as our platform. But there are certain small deficiencies like any simulator has, and modeling, for example, the effect that your CD changes with Mach number is really difficult to do when you just use PlaneMaker. So we've decided, look, we use the X-Plane flight model, but we override it in those points where we think we can do better. And that's what we're doing here. So that gives you the correct drag, gives you the correct lift, you have the correct thrust. And with those things together, you automatically have the complete correct end-to-end performance from takeoff to landing. Your fuel burn for those conditions will be very, very close to what you get with a real aircraft that you fly with the same speed, same wind, etc. And then, of course, the handling component. We started developing this a long time ago. So our flight control laws have been improved based on pilot feedback for many times. So in the meanwhile, I'm fairly confident to say that the handling that our aircraft provides is as close as you can get on a desktop sim. Of course, your joystick always plays a big role. When you ask a pilot, depending on the joystick you put, you will have a very different experience. But the rest that's independent from the joystick is as close as you can get. The second part that I really like, because that's my professional background, I've been working at Bombardier in aircraft systems for 6 years, just before COVID hit, is the systems of the aircraft. So what we try to do is we're not just simulating the cockpit effect, we simulate the underlying physics. So like one of the advantages that gives when you inject the fault and you have all the underlying physics correct, the effect of the fault downstream is going to be correct on its own. You don't need to worry about like, okay, when this happens, then I have to do this, then I have to do this, then I have to do this. It all happens automatically just based on the model. And pretty much most of our systems comply with that now. So whether you take the bleed system, the air conditioning, hydraulics, electric, they all are subject to this rule that we really have the underlying physics modeled in our aircraft. And then the third component is, of course, usability. a big one is situation load safe. We had that in our aircraft since the first release of the A319. So you can leave your flight, shut down your computer, 3 days later come back and say, I want to continue it. Or you can also say, I want to do this landing a million times. So you can do it again and again and again until you get it right. And the situation safe, it's going to give you the aircraft in the exact state that you left it in. So the flight plan is going to be there. All the systems are going to be the exact same state that you had them before. There's nothing you need to configure again. Everything was the way you left it. And that comes also with the autosave. So if ever X-plane should crash, you can just say resume flight, and then it's going to continue from last autosave, which is a configurable time before the crash. So you can do, like, I normally have it set to every 5 minutes, but you can bring it down to every 1 minute if you want to. And then, of course, we always appreciate user feedback. Sometimes functions take a bit longer before they can actually make it into the thing. We all have to decide where we use our resources the best. But like people were asking for a CPDLC, so we started putting it in. We have an in-cockpit printer, where you can, like, for example, when you have your takeoff data, you can just print them with the printer. You can put the piece of paper in front of the thrust levers and you can see all your takeoff data there. Don't have to go into the MCDU for that. And we also have introduced this interactive audio control panel that you can use in order to fly without ever opening our menu, which is normally used. You can load the airplane, for example, through the menu, but you can also use the IACP. You can tell the cabin crew to chuck passengers out or add new passengers. You can tell the baggage loaders to add additional cargo, etc., through that little interface at the bottom. And when you look at the 3D model as it is today, all the sounds, and you compare with what we released initially 5 years ago, it's like also 2 worlds apart. So we work on that side all the time too, in order to give you guys the best possible experience. One example I would like to give for how deep we go in the system simulation. I actually have 2 examples. We have to see if I have time for the second one. But one of the examples I would like to give for the first is the question of real data. That's what I see a lot in simulation. And as somebody who has worked in the real industry, you know that this is not realistic. In a simulator, you always get perfect data. So you look at your indicated airspeed, and that's exactly this indicated airspeed that the simulator currently simulates. In real life, that's not the case. In real life, whatever your speed indicator shows you is not going to be exact value. It's going to have an error. And that error is on any measurement. It's on CAS, it's on attitude, it's on altitude, it's on the position. Everything comes with an error. And this error, the one that we've modeled because it's the most dominant one, is called the offset error. So if you look here, you have the actual real value evolution. Then the air data computer for the calibrated airspeed, air data computer 1 is gonna, for example, in this case, gonna give you a slightly higher value. Can be that ADR2 is gonna give you a lower one. ADR3, in this particular case, is the closest to the real thing, but the computer doesn't know that. The computer in the airplane only sees these 3 values, and it has to live with that because it doesn't know which one is the real one. And yeah, as I mentioned, this is called an offset error, and we model that on every sensor reading that you have in the real airplane, because real aircraft have this effect too, and I think it's important to represent that in a simulation. So, and these are random. So like every time you start the airplane, we decide a bit differently what error is going to be on what reading. So your experience is going to be slightly different every time with respect to, has the co-pilot the higher altitude? Does the pilot have the higher altitude? Because this is what effectively happens. You can see here, you're flying, the left PFD is co-pilot, as pilot, the right PFD is the co-pilot one. And you see the left, we have autopilot 1 engaged. So autopilot 1 means it closes the loop on all the pilot side data, which is why on the pilot PFD, you see you're perfectly on spot on 250 knots and you're perfectly at 360, at flight level 360. The right side, however, thinks that our speed is a bit lower, so you're 248, and your height is a bit lower too. And again, this is something you will see in real airplanes also. The effect here is a bit like it's the most extreme I could find. Normally it's a bit less, but again, it's a random function, so each flight is going to be a bit different. And one thing that's important, also we apply the error at the actual measurement. So for like CAS and altitude, for example, we don't apply it on the speed that you see, we apply it at the pressure measurement. So we take, this is my total pressure, this is my static pressure, and then we derive everything you see from those values, just like it's done in the real airplane. And the advantage of doing it like that is if you say, this sensor always reads 0.1 millibar too high, the way how this error scales into your final reading is again automatically applied by the simulation. So, and as I mentioned before, each autopilot uses the on-site values for control. So if in the scenario you see here, you switch from AP1 to AP2, you're going to see the airplane accelerate a little bit until the co-pilot PFD matches exactly the right values. And then fly-by-wire has a big question, which values it's supposed to use. And there we use the same voting algorithms you use in real airplanes for that, which then determine which of those three values is the one my fly-by-wire system is supposed to use for its closed-loop control. One example also where this is important is we provide satellite landing system functionality. And effectively what that does in real life, it reduces the error on your GPS position. Like if you have an unaugmented GPS, your position error can be 50, 60 meters. So you're landing next to the runway if you use it. With this SLS system, that error gets reduced to 1 meter. And that's exactly what happens in our airplane if you choose to do a SLS landing. As soon as it engages on this SLS, it's going to reduce the GPS accuracy to this 1 meter. And like that, you're actually going to hit the runway as you would like to do. Okay, how much time do I have left, guys? 5 minutes? Okay, I might be able to make it to this because this is actually a very important feature too. And I have to do a little excursion into flight physics for that. We have a full actuator control hinge, actuator control surface model. So your control surfaces don't just work like the computer says, I want it at 20 degrees, and then you move it to 20 degrees and leave it there. We actually have the full system model with the actuator and the surface attached to it. So, and for that, in order to go into details there, I just want to introduce two technical terms. What's a hinge moment? The hinge moment is effectively the aerodynamic forces trying to turn your surface around its location of rotation. The location of rotation is called the hinge line. And yeah, your aerodynamic forces, for example, in case of the wing, you have less pressure on the wing, more pressure below the wing. So the forces will try to push your ailerons up. So for example, in the case of an aileron, the actuator has to actively hold the aileron down. Otherwise, it's not going to be at the zero position. And that force or moment, because it's a rotationary force, is called hinge moment. And the job of the actuator is really to bring up the hinge moment to get the surface where you want it to be. So the two takeaways from this is there's one position. If I now cut the actuator away, the surface would move in response to the hinge moment to somewhere where that hinge moment doesn't exist anymore, right? Where the airflow is exactly where it floats to the position where the airflow wants it to be. That position is called the aerodynamic neutral position of the surface. And this is rarely zero. And I checked that on how our airplanes does it and how other ones do it. And you'll see that when a surface gets disengaged, very often you'll see they just stay at zero. And that is not realistic because when a surface is disengaged, it will always go to aerodynamic neutral. And a second thing that's important is the further I want to move my surface away from aerodynamic neutral, the more force that actuator has to do. It's pretty much a linear function actually. So twice the deflection means twice the required force from the actuator. And we model all of that. So we have even the surface weight and the inertia in it. So we have the actuator, which then we have hydraulic flow through the actuator, which then drives the force, and the force accelerates the surface to go, etc. And you really have a full second order system. And then at the end of that system, we close a loop around it. We drive the valve and the actuator to the right position until the surface is where it's supposed to be. And that system works reasonably well. So you guys as a user, you're not going to see it. So then the question is, why the heck did you do it if we as a user don't see it? And that's where it becomes interesting because as soon as you have failures, there are going to be effects that you will see, which you cannot model without having this model in place. So if, for example, I fail one actuator in my elevator, and then you pull all the way, you'll see the surface is not going to go all the way because the single actuator is physically not capable of bringing up the force to get it to a full deflection. And if you just have a basic model, your surface will go where you want it to go, but with our model, it doesn't. And the second important thing is if you have lost, for example, an aileron, both actuators are disengaged, it's not going to stay at zero, it's going to go up. And going up means less lift on that surface, and it also means a pitching moment. So it has an effect on the aircraft behavior. So this here is, for example, I failed the blue hydraulics, I failed ELAC 1, and in that case, you lose the right aileron. And without this type of model, the aileron would just simply stay at the neutral position, but here you can see it has actually moved up to like 3-4 degrees trailing edge up, which has an impact on your performance, on your pitch balance, etc. The left one follows suit, but that's an active thing from the flight control system that tries to keep your wings level. So that's why you see the left aileron at the right position of the right aileron, but the physical effect of floating to aerodynamic neutral is visible here. And that's in cruise. If you go to lower speeds with higher angles of attack, this effect will be significantly more severe. Another bonus of this model is actually when you park the aircraft on the ground and you cut off all hydraulics. You always see the surfaces droop in real life. This model takes care of that for us. We don't need to have extra logic that went on ground and park droop the surfaces. All this happens on its own. And if you look at the rudder, depending on the direction that the wind is coming from, you'll see that on our aircraft, the rudder either goes left or goes right, because again, this model takes care of all of this by applying the hinge moment that is induced by the wind onto the rudder surface. And the second case where this becomes really interesting is if you fly dual hydraulic failures. So here I did a dual hydraulic failures and I didn't do the procedure. So I dropped the landing gear 200 knots, which on an Airbus gets you to direct low. And then I slowed down to my approach speed of 160. And that means my elevator, in order to maintain this attitude, is not zero, right? You can see on the elevator there, they actually deflected up, like the one elevator that's left is deflected up like 3 degrees. And I didn't use manual trim. And when you look at the pressures, there was a pressure before, sorry, I'm already at 50% load just to maintain flight. You can't flare anymore. There's no authority left. So the landing in this scenario was pretty shitty. I had 3000 PSI. You can see like full power on the actuator. This is how far the elevator got. It didn't get to the stop and the airplane didn't flare. If, on the other hand, you do the procedure and you trim out your elevator that it is at zero, you will be able to flare. And again, these are effects you can only model when you go to this level of detail. Otherwise, you won't see these effects on your simulator. The last one, I think he wants me to get finished. Another one, it's not unique anymore, but it was unique when we came out, is the situation safe, as I mentioned before. This is the airplane dark and in the cold and dark state. I said, okay, loads tutorial section 5. It loads and it has everything. It has the entire flight plan. It has the engines in the same state, the APU, hydraulics, electrics, everything is in the state that it is supposed to be, or that it was in when I saved the tutorial section 5 complete situation file a year ago, actually. And the big question, what is gonna be our next airplane? So these are all the Airbus aircraft with fly-by-wire that exist. These are the ones that we have done. The Flight Factor A350, we've already publicly announced that we will work with Flight Factor to get that one, so they'll get our systems, but it will be Flight Factor for like EFB and 3D model. And pretty much it's gonna be one of the other ones. That's as much as I can tell you. Okay.
That is such a tease.
Sorry.
It's one of these Airbus aircraft. Amazing. Thank you very much. From Torsten, from ToLiss. Unfortunately, we don't have any time for a Q&A, but what I would recommend maybe you doing is just hanging out outside of the auditorium. And for anyone who does have a question for Torsten, please please feel free to come and find him and ask him any questions. Thank you so much.
Thank you.
Amazing. Thank you.
Thank you for having me.